Okay, so in the previous chapters, like chapter 1 until especially chapter 4 to 6 is the we call it the material balance or mass balance, that you will have the midterm, right, in this Thursday, right? So that should be mass balance. So aside from mass balance, the part of the course that we will going through is the energy part, or energy and energy balance. So first, we are going to at least define what is energy. And for some reason, if you are quite really fascinating about physics, or especially energy, up until now, scientists or any physicists still not really sure how to define energy. But they are pretty sure how to convert energy from one particular shape to another shape or another type of energy. But how the energy works and where does it come from, still there are some theory, but not really exact. They're not really sure how we can develop energy. But if we think on how we apply energy, as in terms we apply fuel to our vehicle, or we apply some process temperature to our like manufacturing process, like you have in some cases for your study when you are working on like from the basic one, like a physics, you increase the temperature, you boiling the water, you are actually having energy put inside. Okay? So we say that probably if we are calculating based on process, okay, based on process, or any manufacturer, we can say that the energy, or to apply energy, it requires some or we can say probably it's expensive, because we need to have, or we need to increase the temperature in which we need to at least cultivate some equipment or devices, and using some if we want to increase temperature, we need to have some burner or some equipment. Okay. And the idea, okay, for our talks here is basically how, because energy seems, if we take stance that okay, energy is expensive, how to make sure that energy is efficient. So how to make energy efficient is how we are actually, that is our goal. And to know how we can make this efficient, so how we can make efficient, first is we need to know the energy balance. So it's pretty much the same perspective when you are doing the material balance. So you need to have some expectations. You put some mass inside, and you're expecting another mass come out, right? So you're also expecting the outcome. Pretty much similar. So we are expecting to put some, or to apply some sort of energy, and the outcome will be also another energy with probably different type of energy, and that is how we are going to observe. Okay. Okay. So back to the concept of energy. So to understand the energy balance, you need to first develop what is energy in terms of what we have learned. At least the first law of thermodynamics. That's the essentials for chapter 7. So essentials first is the first law of thermodynamics. And to set the forms, if we set the total energy of a system has 3 components. So we are only focusing on 3 components for energy. So the type of energy that we are looking for is the kinetic energy, potential, and internal. Okay, what is kinetic energy? Kinetic energy. Motion. Yeah, that's the key. Motion. Potential. Yeah, the height. That's. What is internal energy?
So every system is made up of matter, and they're in constant motion, and so the sum of the collective.
Yeah, molecular.
Molecular.
Yes.
Yeah, because they're made up of molecular species, and the sum of these.
Yes.
The sum of the energy of these molecular species is equal to the internal energy.
Okay, good. So kinetic, potential, internal. So we can also say the internal energy as aside from kinetic and potential, we can also say that it's internal. But if we are looking why it's called internal energy, because in every aspect, especially if you look on how we get the coal or maybe the fuel, they are actually from the species, right? From the species that is we are digging, like we get the fossils, and then we have they already the chain of the carbon they generate, and then we can extract them into fuel. Right? So it takes like million years, right, for the fuel to be applied, so we can apply this fuel. But nonetheless, it came from life, right? From species. So actually, if you think yourself, like as human, we are also energy. You agree with that? We are also energy. I mean, sometimes when we deal with some problems in physics, in our case here, we deal with energy that is okay. We have fuel, we have increasing temperature, blah blah blah. We sometimes forget ourselves that we are also energy. Okay? When we eat, drink, when we breathe, it's also part of energy. Simple way, if you remember your biology class, probably, you remember that we have small cellular called mitochondria. That's our, how to say, our horsepower. When we have those, then we can produce at least energy when we breathe. So if you take your deep breath and slowly release your breath through your mouth, and maybe put your hand near your mouth, you'll feel warm, right? That means they are releasing energy. So every time we are breathing, our cells are regenerating, and maybe they are, because every day our cells is dying and growing, and that's why we are becoming old, right? So back to here. So if we are looking on the energy, maybe let me go through from each one. Okay. So kinetic, the keywords is the motions. It can be translations or rotation. And for simplifications in our chapter or in our course, we are just focusing on just translation. Okay? No rotations. And potentials is it has potential fields. Let me just write the potential field. But in our case, to simplify our course and our perspective for the chapters, we're just focusing on gravitational potential energy. And internal energy, we can say it's aside from kinetic and potential, and we can add that this is related to motion of molecules relative to the mass or center of mass. So our molecules, our body, the molecules in our body, they are vibrating, they are always moves, they have vibrations, they have rotations, and that's how we can have life. So one way to prolong our life is to have the. I'm not sure if you see in some science fictions, they approach for cryogenic, which means we are froze ourselves, and then 100 years we wake up. Oh, it's the future, like in science fiction. Okay, and because we talks on, I mentioned that we have a system, so it means that we have some sort of domain that we are going to observe. That means first, if this is a closed system, closed system means that no mass transfer, right? Across the boundaries. I think you also learn on the mass balance, right? The closed system. And from here, we can write that energy transferred between system and surroundings in two ways. First, we can transfer as heat, okay, and second, we can transfer as work. So heat means that energy that flows, result from temperature difference. So for example, if you have two temperature, high and low, the energy will flow from highest to lowest, okay? From high to low. Okay? So we can have the flow of energy. And work, we can say it's aside from the temperature difference. So it can be anything. It can be force, any torque, or maybe electric, like voltage. We can also think that as a work. So this is practically aside from temperature difference. Usually, the case for heat and work, we can develop or we can observe through the movement, the piston movement, okay? The piston movement. And the conclusions or the important here. Let me write maybe here. Heat. We can write heat positive, okay, if from system to surroundings. And negative if it is from surroundings to the system. And work is defined as positive when it is done by system on surroundings. And negative when it is done by surroundings on system. So it depends on the perspective. So, but actually, this positive and negative is just it's on agreement. It's on agreement. If you read or maybe learn through other course in other departments, probably they will switch this positive mode. Okay, if you know what it means. Okay. But that's just an agreement. But within our course, in our textbook, we are taking the positive for heat is if we have heat flowing from the system to surroundings, we take it as positive. But it's flowing from surrounding to system, like from outside to inside, and it's negative. And work is done by the system on surroundings. So the who does the work is the system, then we take it as positive. But vice versa, if we are having the surroundings that taking our work on a system, then we take it as negative. Just agreement. And of course,
talking about energy, also talking about the unit system that we are going to apply. Usually calorie, or the British system, the BTU, it's just British Thermal Unit. And they have their conversions. I think you can also check with your textbook. And oh yeah, I almost forgot to write the first law of thermodynamics, which is the conservation of energy. So energy cannot be created, right? It cannot be created, cannot be destroyed, can't be created or destroyed. Okay. So since we are talking about system and surroundings, and we also talking on the first law of thermodynamics, to relate those two terms of the conservation of energy and the system, then we will have, or at least we are having this energy, this kinetic potential internal, and we are looking on the system. We are talking on which energy is in the input and what is the output. Okay? So we are having the some sort of balance equations. Okay, let me go through. But before we talk on balance equation, maybe we can have more discussion on the kinetic energy and the potential energy. So I think, as we have learned for several times during your high school also, the kinetic, we can take it as m and then v squared. Mass and velocity. So it means that the kinetic energy depends on mass and velocity. But if you want to make it clear, it's supposed to be relative to the surface of the Earth. But nonetheless, the mass velocity should be easy to be understandable. Okay. And we can also write the terms into rate. So we can simply say that this is the rate of kinetic that transported into the system. And don't forget that if we are having some calculations, you can confirm your calculation through your unit conversions. That should be helpful for calculation. And The second part is the potential. Which is usually we take h for height, but in your textbook it's taking z. But it's supposed to be similar, so it's height, gravity. Gravity is acceleration, and mass. We can also take the potential into a rate, as in the kinetics. Okay, now from this kinetic and potential energy, we are going to take this into our balance equations. So energy balance on closed systems. As we mentioned, that closed means no mass transfer. So the idea is we have input, we have output. Let me write input minus output. This will have accumulation. This will result, this input and output will result with the net energy transferred. Okay. So we call this closed system based on the mass, no mass transfer. But if we're looking on the energy still can be transferred. Okay? It still can be transferred. So when we have this input and output, the difference between those two will have the net energy transfer. Okay? And it will equal to the accumulations, in which the accumulations is the final system of energy minus the initial system. So the initial system, if we define the initial system, if we define this as the internal energy U, I for initial, plus the kinetic, and plus the potential. So this is internal kinetics and potential. And same way, we define the final system as U, F for final, plus kinetics F, plus potential F. Okay.
Sir,
Yes.
the balance, the energy balance, why isn't there a generation term?
Which one?
Input minus output is equal to accumulation. Why isn't there generation term?
Generation, which you mean?
Like a generation, like say we have a chemical reaction occurring within our system, like this chemical reaction can give off energy. So why don't we have a generation term to like account for like the energy that goes on, like that happens within our system?
Actually, we have the general terms as in accumulations. This is actually the general how to say, the general equations for the energy balance. So we are actually trying to step by step to looking at what we have in the system, and we are trying to take it into our balance equation. So we have, for the previous one, we have the internal kinetic potential, and also we have the work, right? The work that can be done by the system or done by the surroundings. And this work is actually the other side. Okay, I'll write here. So we have the energy that transferred, the net energy. As the heat minus the work. Now, if we look on all the equations, final and initial, and we are trying to subtract each of them, we are subtracting each of them, then we will have okay. This Q minus W is actually signifies the positive negative terms we are agree on in the first slides before. So we can transfer energy as heat and work, and this is simplified to be based on our agreement on where does the works come from, like is it done by the system or is it done by the surroundings, and heat whether it's going to have from the system to surroundings or from surrounding to the system. Okay, so we are having just the default in the default. In applications, it depends. Okay, it depends. It depends on what's the case. Okay? But let me just write the default like this. Okay? And we can take this subtraction into a delta. So we call this is the delta U plus the delta of kinetic energy plus the delta of potential energy equal heat minus work. We can say that this part of equation, this is the default equations for basic form of first law thermodynamics for closed system. And of course,
since it's the basic one, in a case, you need to be wary on the signs, each information. Okay. So, for example, if I take some notes here, let me write notes that the U, or internal energy of system, depends on chemical composition, and temperature. So if no temperature change or phase change, means that the chemicals stay as it is, or any chemical reactions occur in closed system, and if the pressure change, but it's just a little atmosphere, change a few atmosphere, then the delta is 0. And then similar with the other sections like kinetics. For example, if there's no accelerations, means that it's just fixed. So we can make it as 0 because final and initial is the same. Okay. So the kinetics can be 0 if no acceleration. Or maybe if the system, is better. If system is not accelerating. And the potentials is 0 if system not rising or falling. If the system perfectly insulated, means that there is no heat. You can say the heat is 0. It's the adiabatic, right? Adiabatic process. If you remember, so I think you can remember I think in chemistry, like the isobaric, adiabatic, okay? Isovolumetric, okay? That's the ideal gas, right? When you learn ideal gas, like pressure, volume, and R, T, right? You learn on when you change the temperature, what will happen when you have constant here, what will happen. Okay, if or Q is 0, if the system perfectly insulated. Or we can say that system has the same T as surroundings. And work is 0 if there are no moving parts. or electric currents, or any radiation at system boundary. Okay. Okay, for example, okay, to let you know how to apply this balance equations, let me give you an example. If I crop this, okay. Should be, this is gas contained in cylinder with piston.
It's piston here, and it's heavy. It can be moved. We have initial temperature 25. Place in boiling water. Blah blah blah. Heat in the amount of, so we have heat 2 kilocalorie. Transferred to the gas, and it equilibrates at 100 degrees Celsius. The piston then releases, and the gas does 100 joules of work. So gas does the work in moving the piston to its new equilibrium position. So it's moving. The final gas is 100 degrees Celsius. I'll write the balance equation for the 2 stages of this process, and each case solve for the unknown and determine the equations. Consider the gas in the cylinder system, evaluate the change in potential energy of the gas as the piston moves vertically. First, okay, so we can ignore that and assume it's ideal gas and express all energy in joules. So maybe, for example, if the problem, the self problem, if there's not mentioning any conditions, you can assume it's ideal. You can assume it's ideal. Okay, so first looks on, we have 2 kilocalorie. The first initial is 25. Final temperature is 100 Celsius. And we have 100 joules of work. Okay. So we can, let me put wrong here, this one. So first we can see the initial and the final state. So 25 and becoming 100. And we can write down the formulations for the balance equation. This is 0, this is 0. And work 0, right? No moving boundaries. So we have the delta, and we can have, since we have our heat is 2 kilocalories, so we can take this into 2 kilocalories. Or if you would like to exchange to joule, you can also changing to joules.
So we are changing to 1 joule. We have some conversion, and this is the joule for the energy. Okay, one more here. Let me finish this. And then we have the work that has. Okay. So from initial state 100 Celsius, final state 100 Celsius, but it's moving. We have delta U plus you can say this is 0, this is 0, and then the internal energy now is 0. So this is the second process, right? The second process, and we have the Q is equal work. So the work is, or rather, the work is 100 joule. So Q is 100 joule.
So in the internal energy, 0 if the change in temperature.
Is there any temperature change?
Started at 25.
No. This is we have two processes. So we need to separate the process. The first process is 25. We already done that. The second process from those 100, there is work that has been going on, right? So this is the second process. So whenever you have like a problem, you need to at least take it into some process. If you are dealing all into one process, you will be confused on which part you are going to check. So instead, we having some sort of process, and it will be elaborated more in the I think next part. That is, we have the some process. If you remember some chemistry, it's basic chemistry actually, and you have like different way which part you are going through, and you can take specialized. But actually, I will just stop until here. We'll continue on and see on the. I think we can finish on next week for chapter 7. So another 2 meetings we can go on and having some exercise. Okay, so see you next week, and good luck on your midterm.
We just got an email that said that our classes are moving on.
Oh, really?
Yeah.
Okay. I will check that out.